My name is Nur Izzati. Let me start by giving a quick overview of why FinFET scaling became important. As we kept shrinking MOSFET, the older planar structure started running into physical limit. The gate could not control the channel properly anymore, and that caused issues like leakage and unstable switching. So the industry needed a new structure that could maintain control even at very small dimension. FinFET solved this by lifting the channel up into a fin shape and wrapping the gate around three sides. This simple structure change gives much stronger electrostatic control. It's the main reason FinFET replaced planar MOSFET at advanced technology nodes. The figure 1 shows how device structure have evolved, starting from the flat planar MOSFET, then to the tri-gate FinFET, and now moving toward GAAFET. Each step improves gate control as the device scales. Now looking at the structure in a bit more detail, a FinFET is essentially a vertical fin that acts as the channel. Because the gate surround it from multiple sides, the device behaves much better when the channel length becomes very small. However, the performance doesn't depend on just one dimension. The fin width, fin height, and gate length all interact with each other. For example, making the fin narrow gives very good control, but it also slows down the carrier. Increasing the fin height gives you more current, but it can create more heat inside the device. And shortening the gate length improves switching speed, but it also increases the leakage and electrical stress. So the main point here is that scaling a FinFET is a balancing act. Improving one parameter may create a new challenge somewhere else. This table summarizes the important geometric parameters and what they influence. Instead of memorizing the number, it's more useful to understand what each dimension does. Gate length mainly affects how fast the device switches and how much leakage it has. Fin width controls how well the gate can hold the channel in place. Fin height determines how much current the device can deliver. The outside thickness affects how strongly the gate can pull on the channel. And the fin pitch tells you how close the device can be placed on a chip. All these parameters work together to define the final performance and reliability of a FinFET. So when engineers scale the device, they doesn't shrink everything equally. They selectively adjust this dimension to maintain the right balance.
Let's discuss about impact of channel scaling on device performance. Channel scaling in FinFET is all about shrinking the fin width, height and gate length to improve control. When fins are narrower, the gate has stronger control over the channel. This suppresses short channel effects and leakage currents, which are major issues in traditional planar transistors. Taller fins compensate for the reduced width by increasing effective channel area. This boosts on-state current and makes switching faster, which is critical for high-speed logic circuits. However, aggressive scaling introduces threshold voltage variability due to quantum confinement and random dopant fluctuations. This means device may not behave identically, which complicates circuit design. Finally, while scaling reduces leakage, it increases parasitic capacitances. This trade-off can limit RF and high-frequency performance, so designers must carefully balance dimension. And to conclude this, channel scaling improves performance by enhancing control and speed, but it introduces variability and capacitance challenges that must be then managed. That's all. Okay, let's discuss about reliability implications of channel scaling. In this, performance gain from scaling can come from at the cost of reliability. Smaller dimensions mean stronger electric fields, which accelerate degradation mechanism. So the first point is bias temperature instability, BTI. In this, narrow channels increases stress on the gate dielectric, causing threshold voltage shifts over time. This reduces stability and device lifetime. Second point, hot carrier injections, HCI. This explains stronger fields energize carriers which damage the oxide and create traps. This leads to faster aging and reduced drive current. Third point, process variability at nanoscale dimensions, even tiny manufacturing variations causes big differences in leakage and threshold voltage, making circuits less predictable. So the fourth point is soft errors. In this, reduced capacitance makes devices more vulnerable to radiation-induced errors, which can corrupt data in memory and logic circuits. Last point is aging effect, TDB, which is time dependent dielectric breakdown. In this, the thinner oxide breaks down faster under stress, leading to leakage and eventual device failure. So, to conclude this, channel scanning boosts performance but compromises reliability. Thus, designers must adopt reliability aware models and error correction strategies to ensure long term stability.
Discussion. Continuous scaling of CMOS technology has led to a highly shrunk dimension, resulting in huge variation of dopant and trap distribution, which impacts both time zero and end of lifetime EOL variations. The BTI degradation demonstrates the random variation is dominant rather than the systematic factors. Experimental measurements comparing paired SRAM transistors across multiple wafers and lots reveal only a weak wafer-to-wafer and lot-to-lot variation for both pull-up and pass gate, confirming the dominance of random device-to-device variability. Furthermore, an absence of correlations between the BTI-induced change of voltage threshold and the time zero threshold voltage, indicating that the defect charging of creation processes are stochastic and uncorrelated with initial variation. The defect-centric distribution, and also known as exponential Poisson distribution, as a robust candidate to accurately describe the variability of both BTI and HCI in advanced FinFET, has also been validated. This is based on the concept that device degradation arises from a Poisson distributed number of charge defects in each device, where each defect contributes an exponentially distributed shift to parameter. Defect-centric distribution has matches the silicon data well for HCI variability attributed to similar trap behavior with BTI. To conclude our report, continuous FinFET channel scaling offers better electrostatic control and performance improvement, but it also has a drawback in that it increases internal electric fields, which hasten reliability loss. This scale intensifies important degradation mechanism, mainly bias temperature instability (BTI) and hot carrier injection (HCI). Time-dependent degradation is dominated by random, also local variation rather than systematic variable, according to reliability analysis, which also shows no link with time zero threshold voltage. Therefore, the defect-centric distribution, also exponential Poisson distribution, must be adopted in order to guarantee FinFET viability. It has been confirmed that this model is a strong contender for describing the stochastic variability of BTI and HCI. For precise end-of-lifetime EOL reliability prediction that meets strict low failure requirements of advanced technological nodes, the defect-centric model is necessary.